EM. Due to the time we only have 10 days, so it's really difficult to cover everything. So we try to focus everything on EM, but in this data processing, I will expand that a little bit based on our research experiences. We'll expand that to ultrasonics. So you'll see one of the lectures I'll talk about mainly on guided waves ultrasonics. There are other applications like for composites that will deal with multimodality methods. Right. For metal, you also see it's a it's a very mature field because before we actually have lightweight composites or new materials emerging in the field, that people spend a lot of time understanding the metals and the responses of signals from the metallic structures and materials. All right. So I highlighted three major aspects that we are doing here in terms of research, and this is also going to be covered in the GIAN course. So the idea of an efficient and a good teaching, effective teaching, I believe this philosophy that we always have to stay at the forefront of research, right? So we are going to teach the course based on the ongoing research that we're having here at Michigan State and cover the fundamentals in inverse problems, sensors and systems, and also prognosis. So for inverse problems, what is inverse problem? We'll talk about that in this GIAN course. One simple application of that is we can use inverse problem approach in NDE to determine the defect profile, for example, and based on the measurement from the NDE signals, based on different geometries, based on different setup, that we can actually have a better understanding of the data using inverse problems. So think about the four problem I just mentioned. For the inverse problems, now you start from the data space. So we'll deal with a lot of data. Then we will do the inverse problems and try to go back to the physical space, right? So in my PhD thesis, which is about 13 years ago, that I proposed this closed loop. So you have actually a closed loop from the physical space for problem to data space, and from data space inverse problems going back to the physical space. Other inverse problem techniques, including the signal image processing, I know for graduate level class or maybe multiple courses, that as an engineering student, particularly in ECE domain, we deal with a lot of data processing. The data can be 2D, can be 3D, and sometimes it's just simply 1D or higher dimensional. So we do a lot of data or signal image processing for inverse problems. In this course, we will particularly cover a technique called time reversal technique. So I'll use a very interesting application where I call it signals in the soil. So it's a agricultural application. You'll see, why ND can also apply for precision agriculture, or we call smart ag or smart agro system application. Of course, you've learned numerical modeling. Maybe just briefly touch that in the first course. So we're going to also have the model-based inverse problems, where you'll see both iterative and non-iterative algorithms. I believe Professor Rao has posted the materials I shared for the iterative and non-iterative algorithms for NDE and the imaging. I will have my second lab assignment based on that. So I will talk about that in the afternoon today. Well, sensors and systems, I will use a couple of applications, and actually the application here plus some ongoing effort at Michigan State. You'll see some of the fascinating research here that we can demonstrate my inverse problems concepts, talk about in this GIAN class. The last is a prediction. this deal with a lot of data and models. So how we can estimate the remaining useful life.
Hello?
Yes. Yes.
Yeah. Actually, I didn't share it. Should I share it in advance? I mean to say, I thought that we'll be having the lab sessions from 2:30, or should I share those material of the lab one in advance, or I'll share it as per that?
I think you can share this after class. That's fine.
Okay.
Yeah, share that maybe before the afternoon section, so everybody can take a look at it. And I will talk about that when I go over the lectures in the afternoon. Thank you.
Okay, I'll share it. Yeah.
Yeah. I believe you guys have a share folder, something like that. You can all the student access that and download, right?
Oh, or I'll prepare a Google Drive, or you can share it on me on Google Drive.
Okay.
Yeah, I'll allow them to access those folders from the drive itself.
Okay. Okay. I will just leave that to you so you can find the proper way to share.
Yeah.
Good. So for the prognosis, basically we deal with the prediction of our ND signals, and we can estimate the RUL. And the overall goal is try to get the assets management. And most of the time, we want to achieve the optimized maintenance strategy for a complex system. And this is usually called a decision-making level. And I'll talk about that more when we touch the fundamentals of data processing and inverse problems here today. Very good. Any questions, feel free to speak up. I think let Professor Rao know. And I cannot see the chat window. I hope I can see that, and also the question live, but I cannot. Let me see if I can do that. Oh, maybe I can. So if you have any questions, feel free to type in here. I will try to address it. And Professor Rao can unmute you. Okay, so first of all, let's talk about the challenges here. This is the challenges for the NDE overall, and particularly we'll talk about data processing and inverse problems here. So if you look at the society, I think US probably has this problem more significant. And then in India, I know there are a lot of infrastructures being developed, so a lot of things probably are still new. But for the United States, we have an aging infrastructure and systems, right? So we want to make this system to be more resilient, more safe, and make it into a true ecosystems. But aging is inevitable, just like our human body, right? So our human body is aging over time, over years. For those complex systems, aging over years as well. Well, for some systems, the time scale is different. So during this aging, and for NDE, we call this in-service life of a system, that you will actually dealing with a lot of challenges. One is try to understand the materials, right? That's why people spend a tremendous amount of time in material sciences to understand at the material level how they will change over time. And most of the time, you use the name, use the term degradation, right? The degradation of materials. Well, now you'll see, due to the advances in materials, you'll see new materials coming out, and that makes the things, good and bad. The good is, well, you can do a lot of things that you cannot do before with the emerging materials. And also the new way of doing manufacturing. Think about 3D printing, right? So in the additive manufacturing, that you are now using the new way of looking at the materials and try to do innovative manufacturing, for example, 3D printing. But the problem is we still have limited understanding of those materials. Let's say we have a new 3D printed structure. It's metal, it can be metal, right? It can be plastic. For metal, if you look at the microstructure of that, and the microscopic form of that is very different from what you did in a classical way of doing manufacturing, right? For example, using forging or casting and so on. So how we can understand that? This is still a challenge here. And believe it or not, that damage exists in all material structures. Well, this have to go back to the fundamentals of damage definition. Well, if we look at the damage as the material, discontinuities, for example, in the microscopic view, that for example the dislocations in the metal, well, different precipitates in the metal change over time, that we will actually have damage exist in all type of materials. Well, for other like polymers, plastics, so on, of course, you'll see that during the production of a material. So you have different lengths and different time scales. In terms of time scales, that you can have accumulation of damage over time. One thing that I definitely want to avoid as an engineer, particularly for NDE engineer, that we want to prevent the critical damage lead to the failure stage. Well, before it reaches to the failure or the structural system completely has no remaining useful life useful life remaining, can we actually understand this over time? Let me take a step back. That when we talk about damage, we can have a system, we can have a structure with damage in it, right? As long as it can perform what we want this system to perform, or when it is designed. Let's say I can have a system, I can have an airplane with some damage to its structure or material level, but still it can, can fly. It still can fulfill its purpose during, some service it is required to, but the damage is there. So we have to be very clear about, a system with damage, but still it's not at its failure stage. But we have to be very careful here, right? What we want to learn here is how we can understand the damage state of a system and try to monitor that, try to quantify that over time, so we can have a better decision to make. Let's say I have a plane, in a battlefield, that plane has been hit and it returned. Now I have to make a timely decision. Can I let this, airplane take off again, have another task, or I have to repair something, or I have to, ground it to make sure it's safe? So this is actually an idea of a continuous monitoring and inline non-destruct evaluation before the complex system reach to the failure stage. And if you look at the concepts in the military, so I think this is the concept, brought up by defense people in the United States, that we can have damage tolerance concept. I can have damage in the system, but I can tolerate that. Well, if you want to understand the tolerance, then you have to understand this through NDE. Well, if you are close to the failure, you want to predict the failure and how that will happen. And ideally, you want to avoid the failure. But philosophically, I will have to admit that it's almost impossible to avoid failure in our lifetime or in the lifetime of system, right? Everything can fail eventually. But how we can understand the state of the system and try to avoid it. And I know I won't quote a famous person said, it's not me, it's from Albert Einstein. And he said, the smart people avoid problems instead of solving the problems first. Okay, so I think he said genius avoid problems. Smart people solve a problem, genius avoid the problems, right? So how we can do it? NDE is a solution help us to get information throughout this process. Help us to understand the concept of damage tolerance for complex materials and systems. Well, you've learned this in the 5 days lecture offered by Professor Utpal, that you'll see all the problems seen there can be simplified using this simple schematic here. You have some type of MD sensor. You have a structure or materials or sometimes a complex system in front of you, and you can try to inject the energy into these structures or materials or systems, have the energy interacting with the defect, and based on the interaction, and now you can get the signals coming from this interaction and doing the analysis. And that is the fault problem and inverse problem here. Some other domain called structural health monitoring. I would say it's a different research domain when you look at what's been out there in terms of publication, in terms of the conferences, in terms of the let's say it's had a dedicated venue for the SHM, and it can be a dedicated talk when we talk about differences and common about ND and SHM. But overall, I want to mention the key differences here is NDE, usually we will treat this as a local method, while SHM is more like a global monitoring techniques. So think about one energy that you probably familiar with in human medicine or medical devices field. That NDE is more like the MRI machine, CT machine that usually do that locally in a hospital. But SHM is more like the monitoring devices that you can do this over time, doing this 24 hours a day to measure, for example, your heartbeat rate and measure your blood pressure level. And nowadays, you can actually measure more vital signals over time. So this is more like a monitoring problem, right? So that's a very simple analogy when we talk about ND and SHM. Of course, there are more here in these two fields. When we have time over this lecture, we'll try to touch that again. Another thing is we call this damage diagnosis and prognosis. You'll see a lot of these buzzwords out there in recently funded projects. We call this complete understanding of the damage through the detection and prediction. Okay, so if you divided this problem and show this using a damage level versus time, I define the damage, and if we describe the damage using index or some quantified way, then you can show the damage change over time, so you have a better understanding of the materials or system state. And this is called awareness, right? So we can have a material state awareness problem, or we can have a damage index over time. And the dots here are the NDE measurement or SHM measurement, right? So you measure that and it correlates with your damage level. Hopefully, that's what we want to do. And when we are doing diagnosis, you're looking at the second, the left half, that you are trying to understand the damage level using our NDE measurement. For prognosis, we try to do prediction and how this damage level is going to change over time, where we don't have actual NDE or SH measurement. So how we can do the data analytics to do it, to understand the system performance over time. Let's say I have a nuclear power plant, and I have some measurement from NDE or SHM, and I want to tell people, hey, instead of doing this, scheduled regular maintenance, can you do this through condition-based maintenance based on my prediction? Or something is going on there based on the measure data, you need to have some urgent maintenance for that particular components. So that's the beauty of an effective prediction or prognosis of damage. I just want to show you some data. These are the fatigue problem in the GFRP glass fiber reinforced polymer, where we use NDE method to measure the damage progression over time. So you can see this is a lab environment measurement. You can see the damage change over time from 0 cycles to 3,500 cycles. You can also see for the carbon fiber polymer samples that we use ultrasonic measurement to understand how the damages change over time using a colorful representation of the data, where we deal with a lot in the imaging and data processing in this course. Okay, so I think I spent 30 minutes to cover a very good overview of what we are going to talk about in this course. And if there are any questions, feel free to type that in the chat window. Well, now I want to go to some of the fundamentals. Spend another probably 15 minutes on that, so everybody will have a good understanding of the fundamentals. Then we'll talk about the the reading materials Professor Rao gonna share with everybody. I want everybody to read over the 5-day course, so things will make more sense after that. A quick overview of the forward problem. You've talked about electromagnetic NDE modeling. Well, of course, the NDE modeling can be other physics, right? It can be ultrasonics, it can be optical, and so on. So for EM modeling, why we want to do that? Well, let's just take a example. For example, we deal with composite materials. Well, composite can be glass fiber, can be carbon fiber composites, and so on. So it's a very complex geometries, right? It's not going to be a homogeneous isotropic material or geometry. So you're dealing with layer structures, you're dealing with anisotropic materials, and we need to understand that. And simulation model is a very good tool of doing that. If you have a good simulation model developed and did it. Also, we have to deal with complex materials. We have conducting or dielectric materials. For composites, a good example, for example, for the CFRP, you can have the matrix type of composites where you have the conducting carbon nanotube, carbon fibers, carbon fibers, while surrounded by the dielectric materials like resin there. And how we can understand that? Complex composition. You may have linear or nonlinear ferromagnetic. For example, one very classical nonlinear material is a ferromagnetic material. And I will use one example in the Yes.
Sorry. In case of complex composite materials, does a single layer also have nonlinear properties associated with it, or is it that each of the layer has different properties?
Well, this is a very good question. So let me try to answer your questions in two ways. One is, well, when you have your composite fabricated or made up, first of all, you have to understand what type of composite it is. Let's take a simple composite structure. Let's say I have a 0, 90, 0 degrees composite layup. And in that case, then each layer, the only difference there is you have a different orientation of the carbon fibers. And if you look at each layer or every 0-degree layer, that you can treat them to be the same layer when you do the simulation. And you actually validate that in experimental testing. Well, for some materials, it's more complicated. And this is a different concept when we talk about linear or nonlinear, because nonlinearity, in this case, has nothing to do with the way, for example, here, we lay up and fabricate the 0, 90, 0 composites there. It depends on the material properties that we're dealing with. And some of the materials, you can approximate that in the linear domain. Some of them, you have to deal with a nonlinearity at the material level, which will result in the different ND responses. So hopefully I answer your question that, well, let's look at the complex materials, the complexity in different ways. And I like your question, why I call it good is, let's look at, for example, the material level, whether it's linear or nonlinear, and then let's look at different layer for the composite here, how we can model that. Well, if we have a complex multi-layer layer structures, then if it has some nonlinearity because of that layer structure, then that's another different story. So it's very complicated. I think it's also material application dependent. I don't know if Professor would talk about using actually a new way of manufacturing materials to introduce new concepts of properties. For example, you can also talk about metal surfaces, metal materials, and so on, which is a periodic structure, not necessarily composite, right? But that's a new way of introducing material properties there. Hopefully, I answer your question. But
yeah. She
yeah.
talked about metamaterials as well. So when you mean 0 and 90,
Yes.
has it something to do with the orientation, the
That's
isotropic
right.
and isotropic nature?
Correct. That definitely,
Okay.
yeah, that's the orientation. Yes.
Okay. I got it. Thank you.
Thank you. Very good. Oh, okay. So I like this kind of question or discussion. So anytime, let's do that. Since we have a small audience here, I think we have the luxury to go into the depths for this lecture. And this is also I would like to do during any of my teaching. Okay, then let me continue on the modeling. Then you can also study this simulation in both frequency domain and time domain. Of course, you'll see why we want to do that for different applications. You can understand different type of defects there. And now we deal with a lot of code computing, everything parallel, parallelization using CPU and particularly GPU. And how we can measure different, for example, modeling of U-band using different differential geometry formulation, how to develop a good user interface, so we can actually have industry people more involved. So that's something that we have to deal with in the forward problems. Well, from forward problem, you'll see meshes, you'll see complex geometries, different materials, and you can have beautiful data predicted from this simulation tool. Well, for inverse problems, I'll talk about a few domains of inverse problems in NDE. Well, if we don't have NDE here, inverse problem is more mathematical and broad concept. You can see inverse problem in different applications. But if we limit ourselves in NDE, hopefully everybody has a better understanding for what NDE is. But simply speaking, from a system engineering, I'm more like a system engineer, although I'm in electrical engineering. Is for the system engineering view that NDE, as I said, that we are dealing with a complex systems with input and output data, right? Or what I just said, from physical space to data space. So now, if we're dealing with the data acquired in NDE domain, that we are now trying to start from there to do the inversion. Well, let's start with a few applications, concepts in inverse problems for NDE. First of all is CT, computed tomography or computerized tomography. I think they're the same. You've seen this in medical devices or medical fields. Well, for NDE, you also have CT using high energy particles. Widely used is X-ray, right? So for CT problem, you can have a simple equation dealing with the input and output. Well, the input here is I0L, the output is IL, right? So, or in physics, that's the intensity of your beam before and after it interacting with the material, here represented by a Mason function f. Well, f is a function of a spatial coordinates x vector, and you can parameterize that along the ray, straight line, the arrow here. So x can be parameterized using L, and if you integrate the material or the function f along this L, capital L here, the relationship is nothing but exponential decay, right? Or an integration becomes negative natural log of output over input, right? And you can change this mathematically easily to make this into exponential decay, as I just said, right? Exponential e to the minus alpha L. Well, that alpha attenuation term is determined by the integration of this f over space. Well, based on the system's concept, any object f can be decomposed into discrete points or impulse functions. So we can start with a single point here. I hope everyone can see my cursor. Then the complex object can be seen as the composition of those.
Sorry, there was a glitch in the connection. So I could not get, how did this integral turn out to be a log here?
Well, the log here is actually determined by the actual physics. If you look at a log, this is a E-based log. Okay, so if let's rewrite this mathematically. Let me see. Let me use annotate here. Okay, so if this is E log, natural log, then if I look at this term, we can change this a little bit, right? So we can have e to the minus integration LF dl is the output IL over I0L, right? If you move this to the left, if you move this term to the left, it tells me the output IL is the input times the exponential decay. This is actually determined by the physics, right? Everything here you are dealing with is the absorption and scattering of those energy photon, high energy photon, over space is going to follow exponential term.
So, I meant to ask the physics part of it. Like, so we are assuming that the output intensity is an exponentially decaying function of the input.
Correct. That's right. So that's why you can have this as your signal equation. Okay, this is more like your signal equation.
Is this specific to computerized tomography, or is it a generic equation related to the intensities we're talking about?
This is a generalized equation. We haven't actually talked about tomography yet.
Okay.
Yes. Yeah. Tomography, that is, you have to deal with, multiple rays, right? So the term tomo means slice, right? Then you can actually see this in a 3D way that you can actually slice by slice, view of this data, and to get the 3D volumetric imaging of the object. That's called tomography. But now we haven't actually dealt with tomography yet. Okay, thanks for the question. So when you have this, F, you can decompose that into a single point. If you look at a single point, you do the forward problem called a radon transform. You look at this into a different domain, just like Fourier transform, right? Fourier transform, radon transform, wavelet transform. You have the object domain, which is a function of x bar here, or x vector, and you can actually show this in the new domain. Here, domain is actually, you are looking at this in angle versus spatial domain here. You can radon transform. And if you do this for all the points here, what you'll get is a linear summation of all those points. You'll all see all those sinusoid waveforms from the sinogram, which is shown here. And this is a new way of representing the data in a different domain. And I believe everybody should understand Fourier transform. You can also look at this in the Fourier domain of an object. And you can do the inverse transform. And sometimes this is called image reconstruction, inverse problem, right? So you can get the data reconstructed. For the Fourier transform, and if you do some additional reading, if you know something about, for example, MRI, magnetic resonance imaging, that you are actually collecting data in the frequency domain or Fourier domain, what we call K-space, then you do data reconstruction to get your actual MRI images in the spatial domain. So that's a very similar concept. And I like the question, is this CT yet? Well, for getting the CT, you have to get a sinogram here by covering all angles, right? For all angles, then how to get that measurement? Then in the hardware level, you have to have, for example, for CT, you'll have a ring geometry. So you have all sensors, usually evenly spaced over space. Here, 360 degrees, then you can get the data fully covered the entire spatial domain. We'll have one example, tomography for microwave in my lecture. I believe that's probably in day 3 or day 4. Okay, let me try to move forward. Oh, let me clean this. I don't know if there's one. Yeah, oh, annotation. Okay, very good. Well, the second problem is called scattering or inverse scattering problem. You see this a lot in, early development of radio frequency or radar applications. And you can have, for example, a transmitter, and you can have receiver to be the same or to be different. Well, let's forget about that. But let's only talk about the inverse problem here. You can have an incident wave, and we can have a simple plane wave incident over an object. If we're looking at, for example, micro frequencies, then you have a dedicated frequency band for it. The incident plane wave will interact with the, for example, a dielectric object. It can be metal, it can be dielectric. Okay, it's up to you. But let's start with a space varying dielectric permittivity, object, epsilon. Then the inverse problem becomes, if I can retrieve this epsilon distribution or this object function from the measurement of a scatter field. Well, the scatter field can be everywhere, right, in all directions. And one way of doing that is you can either have a ring, or you can have a mechanically moved or electrically steering receiver to get a measurement and try to reconstruct that. This is called inverse scattering problem. I use a few keywords here, which probably I will not touch this into details, but you can have different way of getting those scatter waves measured. One is you can have a distributed ring here. The second way, you can have a mechanically steering receivers. The third way, you can have electronically steering receivers, right? And there are different ways of doing it, but assume we can measure everything there, you can do the inverse problem here. I list some results from our published work where we can have an Vivaldi antenna here. You can see this is from COMSOL. We have a transmitter, we have a receiver in the 180 degrees opposite direction. We capture the transmission coefficient or S parameters. Based on that, we can reconstruct what's inside this cylinder, which are through two small inclusions there. And in my future lecture, you'll understand this is actually two dielectric roots of a complex routing system of a plant. The third problem, well, I will actually start from a geophysics definition. So we call this a geophysics problem. Well, it's actually a ND problem, right? So for geophysics, people usually deal with underground objects, right? We talk about oil and gas exploration. We'll talk about seismic wave problem. Well, for ND, it's actually the same problem, just at a different land scale. And you'll see this a lot in, for example, ultrasonics, right? For EM as well, for example, ground penetrating radar problem. So you can have a transmitter, you can have a receiver, you can have some object, with different material properties, different shape, defined as capital D here. But based on the measurement from Rx, you're trying to reconstruct the capital D here. And it's better to understand, or easier to understand from a geophysics setting, that you try to see, okay, whether this D is a oil, a natural resources reservoir down there, and you want to characterize the shape of it, the size of it, and hopefully also the materials of it, right? You want to know whether it's natural gas or oil or not. So this is also an inverse obstacle problem, in mass. Well, the last I want to mention is the inverse conductivity or impedance problem. And you'll have your first lab assignment for the EIT. I will give you instruction of doing that. I believe you'll have 3 or 4 days to complete it. Download the software online and try to do data reconstruction using EIT. I will not cover EIT in details. I will give you a lecture on the lab, but I will leave that to you. So you have a very well-developed tutorial online developed by University of Manchester. You can actually download that MATLAB tools, and you can do this EIT reconstruction from there. So we'll do this hybrid teaching. I'll cover as much as I can for 5 days, almost like mission impossible to cover everything. If you want to really cover this, each topic can be actually multiple lectures. But anyway, I will do this hybrid teaching, and I'll leave this to you. I hope you can spend a significant amount of time in offline reading and understand the lab sessions and do this offline. But for EIT, simply speaking, this is called inverse conductivity, which means that you have an object to reconstruct. For example, you can see here a human body, right, with lungs. If you want to do lung imaging, you can actually understand that as a distribution of the resistivity or conductivity over space, rho of x, y, z. So if you put, let's say, electrodes on the human body, here, mathematically simplify this into a square, you can put 16 electrodes here, and you take this measurement on the boundary of this rho object, and you excite signals by applying voltages or currents. We'll talk about that. You see that in your actual lab, what to apply there. Let's say apply voltages there, and I measured from each electrodes and actually measure between each pairs of electrodes. And from that, how I can reconstruct the role of X, Y, D. So this is the inverse conductivity impedance problems where most of the time you'll deal with DC and low frequency problems. Okay. The last slide for the fundamentals is ill-posedness and well-posedness, or ill-posed problem that you probably hear a lot when we do inversion or inverse problems. Well, we don't like ill-posed problem, right? Because that means usually you won't have the unique solution. So to avoid ill-posedness, you have to do multiple techniques, for example, regularization, so you can achieve the unique solution. Well, for inverse problems, another way of looking at it is what you're showing in this XY domain. The left blue object is XY, is X, or the data space or image space. The right is called data space, or use my previous term, the image space is actually a physical space, right? Where you have the object, you try to get the images. The data space is you have NDE data. You have more details in the share material. I will ask Professor Rao to share. There will be tutorials from Professor Temporino, who's my colleague here in the same group. So I just get his permission to share that material with you, so you have a lot of things to read. So you are dealing with a function or mapping from domain X to domain Y, and the key equation I want to use here is this. And this is actually the signal equation I deal with a lot in the NDE problem, and even in other problem where I deal with signals or measurement. So from F to G is forward problem, from X to Y, and from G to F is the inverse problem. And we can mathematically simplify this using this simple equation that G is A of F plus N, where A is an operator, a transformation, or a function. Simply tells you how I can get my data from the measurement. On any problem, you're going to have an interaction of the energy with the object F. And you always have to consider the noise term there. And here you simply using the additive formulation. You just add the noise N to this A of F. And G is your actual data. It can be noisy. So inverse problem is try to reconstruct from G measurement to get your F. And for well-posed problem, that you have to not only have the solutions of this AF equal to G exist when you're solving for F, you also have to make sure it is unique for any G given, and the solution has to be continuous when do the inversion, or you call stability of this inversion problem. And if you look at similar problems you deal with in the fundamentals, let's use the example of Fourier transform, that you have to make sure you have the inverse Fourier transform to be existing, to be unique, also to be stable. Of course, you can deal with other transformations like Laplace transform. You have the same mathematical problem, wavelet transform, and so on. But now A can be much more than that. This can be a forward measurement model. And depends on the physics of NDE, you can have different A defined. For example, microimaging, ultrasonic imaging, eddy current imaging, and so on. Okay. All right. I think that's what I planned. I spent actually 1 hour for the first 10 slides. I think this is very important. This set the foundation of inverse problems. Then we'll go to examples and try to understand those fundamentals. I would like to take probably a 1-minute break here if there are any questions. So you can ask here. And keep in mind, this is a teaching session. All right, so interaction, Q&A are highly encouraged. so we can get them addressed over time before we actually accumulate questions, which is very more difficult to tackle. Okay, so I'll stop here. So any questions? If no questions, also perfectly fine to take a short break. So I can also have some water. Any question?
Noise is random. So here you said that it belongs to Y. So I mean, how are you confining it to this particular space here?
You're talking about noise?
Noise.
Yes. Great question. Well, it depends on how you define your Y or data space, right? Your data space, if you're considering this data space, which will include the uncertainties. Well, uncertainties, one of that is from the noise, and the noise usually it's a random, right? And it's a randomness nature. We usually use that to define noise, and depends on the definition of data space. Of course, you can include the noise in it. Even it's random, but mathematically it's okay to define that space to include it. And you'll see that we have to mathematically define a data space include noise there. Well, the way to mitigate or alleviate noise in our measurement space or data space and make sure that it can be a well-posed inversion, that's a different concept. And
Okay.
dealing with how you're going to deal with this n in this y, but of course you can have this y defined like that.
Okay.
Great question.
Thank you.
Yeah. Any other question? Okay. 10 seconds, then we'll continue. All right. Oh, hold on. Let me continue. Okay, now I will use a few examples. So you'll see both the forward and inverse problems here. After you take the first 5 days fundamentals, so I will try to speed up a little bit on the forward problems, and you will also see a lot of data in the forms of images. The images can be 1D, it can be 2D, it can be 3D. It's more challenging to show higher than 3D dimensions, but it's also possible, right? Sometimes we have high dimensional data. And I'm gonna mainly focus on one type of material here, which I limit myself to composite, right? Because for different aspects of NDE, it can have a very different way of doing forward and inversion. So let's just limit ourselves in composites. And the reason of choosing composites is also emergent materials, right? It's been there for decades, but still this is not a very well understood domain comparing to metals. Okay, so for imaging for composite NDE, that we can have different different methods. For example, starting from low frequency up to megahertz, you can use inductive or you can use capacitive measurement. And physics or mathematically, you can model that using magnetic dipole or electric dipole. When we understand inductive or capacitive, and for the fundamentals of electromagnetics, you can easily understand what is a magnetic dipole, what is electric dipole. You can have a two-particle model to understand that. Well, for high frequency, particularly for 100 megahertz to tens of gigahertz, you're dealing with a microwave frequency, so you can have the far field and the near field measurement. I believe Professor will probably mention about far field and near field microwave, so I use the same application here. Those four sensors are in-house manufactured at Michigan State that we can design our sensor Either it's an inductive, which is showing here. This is inductive probe. We have two coin sensor. It can be a capacitive. This is open plate capacitive sensor, a miniaturized sensor. You can also have microwave. This is a 6-port, microwave measurement that you can have this working in the near field. The key advantages of those EM measurement for composites is you want to have non-contact measurement, so there's no coupling in between. You want to have rapid inspection of composites, and most of the time the structure has large dimensions or physical sizes that you have to conduct the NDE rapidly and also maintain a large standoff distance, that the distance between your sensing system and object should be large. You want to have single access. Yes.
Yeah. I was saying that the differentiation between the low frequency, like from inductive and capacitive probes, is till that frequency, till they don't behave in a radiative pattern. Is it that, or because the radiation may start from, you can say, sub megahertz range too?
Yes, this is a different classification, and you are absolutely right. For inductive capacitive, let's be very careful about the term radiation. Even for inductive or capacitive, you still have radiation of EM fields, but not in a way of like what we're seeing in the radar, right? Those are more like the fringe fields or the fields that's not propagating long distance over space. It's very, difficult to talk about radiation pattern versus frequency, right? For low frequency, you still can have wave propagating in space, or not wave is actually in the evanescent wave pattern, or in the phase wave pattern when we're seeing here inductive or capacitive. For inductive, for example, if we're talking about eddy current, it's not a wave equation. If you're talking partial differential equations, it's actually diffusive, right? It's a diffusion equation. You only have a first order of time derivative there. But still,
is it something like
yes.
that inductive and capacitive probes will be concentrating on sort of a electrostatic type of behavior rather than having a time varying?
It's still time varying. It's not
It's still
electro.
time varying.
Yeah, it's not static, right? It's still, let's say, kilohertz or megahertz, right? It's still time varying field, but you can sometime call it a quasi-static. It's a quasi-static problem, right? And for quasi-static problem, then when we're dealing with Maxwell equations, and it's much easier to deal with some of the terms there. Then you can ignore some of the term, DDT term there. Very good.
Okay.
Okay. Very good. Okay, so I want to show you some of the examples here that you can have GFRP and CFRP sample here. And the GFRP, for example, here are some holes there. You can get a very nice pictures using a capacitive measurement. And you can actually, try to quantify or characterize the size of a defect using 10 megahertz capacitive imaging. Well, for CFRP, you can see the way they lay up this CFRP. This is a 45-degree, 135 degrees layup there, and you can clearly see the pattern from the surface. By using electromagnetic imaging, you can see the subsurface information. This is 6-ply CFRP with embedded defects, fiber breakage there, right? From surface, you cannot see it, but from EM measurement at 10 megahertz here, this is a eddy current inductive measurement, and you can see the fiber, pattern, and also see the subsurface defects there clearly. Okay, so this is one example showing the eddy current capacitive imaging, and Niraj, just like you asked, this is still a time varying problem, right? It's a 10 megahertz problem. And for this, it's not even low frequency. And you know, different people call low frequency high frequency differently when we talk about EM. Well, if we talk about communications, these are still very low frequency here, right? But for NDE people, this is actually, we call this actually high frequency probe, because usually when we talk about eddy current capacitive, we are mostly dealing with kilohertz range. So megahertz is actually high frequency to NDE people. But if I talk about communications, it's a low frequency. So that's something very interesting that we have to make sure that you know what audience we're talking about. But anyway, the takeaway here is that we can have the subsurface information and get the imaging data and do a simple inversion to get the data here. Well, the inversion, I'm not dealing with any iterative algorithms here. Basically, you just form the data, you know, in a way that you can actually have the correspondence of the structure in the 3D space versus the data in the 3D data space. Okay. So you can also see the delamination and non-delamination area of GFRP when we introduce fatigue using this hinge type of structure. And you can see the crack grows over time. We'll have a dedicated lecture on this. Try to use this, understand this using guided waves measurement versus electromagnetic measurement. But anyway, the imaging of NDE is you can actually see from different inductive TR coil, transmit receiving coil, or capacitive measurement. You can measure the delamination progression over time from red to blue. Blue means no delamination, red means there's a delamination. And from different color, you can see the delamination severity over space. So you can also have, for example, impact damage imaged using EM sensor. So this is an example where, of course, the holes can be easily imaged, but when you have an impact to the structure, you'll have fiber breakage, delamination at subsurface level. Of course, from surface, you can see something, right? But how you can actually quantify that using NDE imaging and inverse problem, inversion of that, then you can using the right NDE method here, the capacitive measurement, and you can do the data reconstruction. And we'll have interesting example very soon showing the correlation between EM and also optical technique. While the ultimate method is try to do this destructively, right? You can actually cut it and look at this under the microscopy, then you can see the correlation between different methods of imaging. Another application I just show here briefly, you have the materials, you can read those fine prints there in terms of innovations and benefits. Due to time, I will not read them or go over them. I just want to point out the key aspects of each method here. And for microimaging, you can have a wide range of microwave sensor design and fabrication. And you can, for example, have Vivaldi, you can have a reflect array. It's more like a phase array geometry. In the radar applications, you can have the 6-port, as I just mentioned before, 6-port measurement reflectometer. You can also have material sensor there. And for this is a simple split ring resonator. And there are, publications in our group. I'm not cover metamaterial in my inverse problem section, but you can also refer to papers we published on the metamaterial geometry. But the idea here is everything working in the microwave frequency range. You can have time reversal imaging, where we talk about inversion of it. You can have a diffraction tomography, or you can just look at the amplitude and phase response of it, and you can get different images. For different problems in composite, you can look at the disbounds, you can look at the voids, and identify the targets there in the in the composite or ceramics domain. So you deal with the sensor and circuits design, understand the materials of it, imaging and reconstruction algorithms for inversion, and detection and characterization of defect. Some examples of microimaging for delamination, the same geometry, you can have a similar data, but different physical meaning, right? And although they have the same color here, but the physics here is completely different. When you look at low frequency capacitive, inductive, or high frequency micromeasurement. Same sample, now instead of using capacitive measurement, you can use microwave. And this is a high standoff implementation. High standoff means that the sensor and the objects are actually far away from each other. I don't know if Professor Upa mentioned this briefly, that you can have this data collected in a very fast way in a far field. And this far field technique give you a very good way of doing the damage screening, that you can see the damage over long distance, and eventually can do this in a real-time measurement by dealing with the data, and you can do the comparison between good or healthy and unhealthy structures or materials, and using inverse problems in their processing, you can reconstruct the damage. And from that response, you can do characterization of the damage in terms of size and severity. Right. So this is a high frequency microwave far field imaging. This is a near field in terms of working at. Yes.
Could you in the go back to the next? Yeah.
Yeah.
So in the far field and near field, how does the resolution remain the same?
No, resolution will not be the same.
Okay.
In a far field, the resolution is determined by the wavelength, right? The radiation frequency. So this is called Amber's limit in physics. The Amber's limit tells you in a far field, if we don't talk about metal materials, okay, that the resolution is determined by the radiation frequency or the wavelength of it. It's half wavelength resolution. For 3 gigahertz microwave, the best resolution you can achieve is 5 centimeter in free space. Of course, in materials, even worse, right? Well, for near field, the resolution is determined mainly by the sensor or the probe size, or the way you set up the near field system. So the resolution will not be the same. And usually the near field will give you better imaging resolution at a cost of smaller field of view and slower imaging speed.
So you employ both the far field and near field, far field for screening and near field for better resolution.
That's correct. That's correct. That's one way of doing it, where we can have this hybrid approach. So far field, you can do screening, as I just said, but you really are not dealing with a high resolution data. You're basically trying to do the detection problem, right? And in the near field, you can better characterize it using high resolution imaging. Well, I will talk about this because this is a lecture, right? This is not a technical presentation. For lecture, I would like the students to think more about, what you want to achieve. If you can work everything in the far field, but you still can achieve superior spatial resolution, that would be ideal, right?
Yes.
So how we can achieve that, right? That's a problem still scratching people's head. We have some limited access in different applications. But that's a goal, right? That's a goal that we want to achieve both. So think about that. There's some interesting ongoing research there. Well, for the near field, that you'll have the sensors typically in the vicinity of the material, and this is a project that we delivered to Department of Transportation. We developed this from sensor design, prototyping, computational modeling, forward problems, understand the physics of it, then we can achieve some millimeter near field microwave imaging and MMI sensing. This was actually done more than 10 years ago when I was assistant professor. So you can actually have some publication out there to read. Another thing that I want to talk about is multiphysics. When we talk about multiphysics, then the data analysis and inversion of it will be more complicated. And this is an example where we introduce acoustic generation using microwave excitation. So we call this microwave-induced thermoacoustic. Well, you'll see other domains people using for small animal imaging, biomedical applications other than NDE, and you also see laser-induced thermoacoustic. People call that photoacoustic imaging. Okay, and it's not listed here, but if you want to read, and I believe everything will be recorded, right, Niraj? This lecture will be recorded, correct? Okay. Anyway, hopefully this I think this lecture will be recorded, so you can always, even if it's not in lecture notes, you can hear. Okay, thank you for confirmation. Then you can actually read if needed. So for photoacoustic, you'll see the laser induced. Now we use microwave induced to introduce thermal expansion. Then thermal expansion will generate ultrasonic signals. So why this is called thermoacoustic, and you can get imaging if you're dealing with inverse problem to form the image, and this is the setup we have in the lab. Try to image biological tissues as well as composites. And let me show you some two videos where you can have EM excitation to a composite metal structure. It's a sandwich structure, and you can see the EM introduce thermal expansion, generate acoustic waves propagating in one material. Here, it's propagating in metal. Then the acoustic wave will propagate in the metal, hit the interface of metal and composites, and you'll see if there's a defect in the interface, then the reflected ultrasonic wave is going to be different. So let's play the video. This is just simple video. Of course, we already have more sophisticated, 3D simulation tools to show that. But this is simple 2D geometry. You can see the layer interface here with no defects, and with defects, you can of course capture that. Right. So the acoustic wave is generated by the microwave excitation on the material. Our latest results is published actually last year or maybe 2 years ago on Journal of Applied Physics, where we tried to design a better microwave excitation using coherent encoding. So if you're interested, you can download that paper and read it. Well, optical technique here in CVRC, that we have this optical transmission scanning OTS technique for rapid and non-contact ND of GFRP, and the idea is you can have laser, and the laser will perform more like a ballistic X-ray imaging. It's not X-ray, it's laser, milliwatts laser. Then you can get the GFRP material, which is opaque in optical technique, in optical visual frequency, but it's more like transparent in this particular laser. So you can see the subsurface information. You can see for the OTS measurement, you can have a nice image of this GFRP and try to monitor the damage progression or growth over time. And those small patches here, and I don't know if you can see that, those are the PZT piezoelectric sensor, where we can measure the ultrasonic response simultaneously. Well, from that, you can capture the impact damage like what we've seen before in capacitive in microwave. Now you can see this using OTS. And from this measurement, you can get the data reconstruction and know the different delamination at different depths or different layer of these components, right? This is the inverse problem that you can reconstruct the data from there. I think due to time, I can skip this. This is infrared tomography or thermoelastic stress analysis, where you combine mechanical as well as thermal. Well, thermal is nothing but infrared. If you consider this as EM, this is also one type of EM method that you can actually get the temperature profile monitoring of an in-service structure. Then you can actually monitor the damage, progression or the residual damage evaluation in composites at different energies here. I will have one lecture for this using wireless sensor network for guided wave SHM. And I'm not going to talk about too much on guided wave physics. Instead, I'm going to talk about data analysis and how to use that for SHM. Well, the basic idea here is you can have a wireless sensors embedded in the structure. This is really cool, right? You can either put a sensor on the surface of the structure of system. You can also embed this in the composites. One way of doing that is actually you can, for example, you can have this sensing materials put into this when you actually lay up the composites, then you can measure this either using a tethered or wired, or you can use wireless measurement. But demonstration here, you have to use wire here, so you can have those small wires to measure the embedded sensor responses. Well, if we're doing with imaging and signal processing, from those guided wave measurement, you can actually try to do imaging. Here, this is called probabilistic diagnostic imaging, that you can find the most probable location of a damage by using this probabilistic imaging technique. I will briefly touch this in that lecture, where for the inversion, how we can actually find this location. Another way of understand this is, you'll see this in SHM, is you can actually do triangulation, right? You have multiple sensors, multiple receivers there, then you can do triangulation, then you can identify the defect location using triangulation technique. Or you can doing time reversal by propagating the signals from each receiver, then you can have the signals or energy converge or concentrate at one location. Okay, so this is one way of doing distributed wireless sensor for SHM or NDE. This is another project working for Air Force, where Michigan State developed a GMR array, giant magnetoresistive array, for subsurface measurement. I believe Professor Uba should have mentioned this in her forward or fundamentals of the EM NDE class. There we can do surface and subsurface imaging of the defects. Here, the defects actually originate from the rivet. We call this a CUF problem, crack on the fastener. So you have fasteners to fastener structures where you can have rivets to join the multi-layer structures of aircraft body, right? Aircraft body is going to be a multi-layer structure, so you have those structures, rivet structures there. So you have defects originated, and the challenging one is coming from subsurface, right, on the fastener. So this is a CUF problem. This is a project, actually, we received several funding, and we're actually submitting new fundings to NSS as well. And this is called underground pipeline network. It can be either steel or plastic. And we typically focus on the distribution pipeline network. Distribution means the diameter of a pipe is smaller comparing to transmission. So this becomes a unpickable problem. I don't know if you guys are familiar with pig or piggable. Pig is not the pig. Pig is called pipeline inspection gauge, where you can see here we can have a robot for the unpickable because it's very complex and small diameter. For large diameter transmission line, you'll see those pig devices were equipped with MFL, magnetic flux leakage. You've learned that in the first module. Equipped with eddy current, equipped with ultrasonics, and you can move inside the pipe and take the data and do the imaging or sensing of it. But for complex distribution pipeline networks, they will have to use robotic technologies, right? I wish I had more time to talk about this. This is a very interesting field, and I believe in India, in a lot of Asian countries, you know, when we have more infrastructure for underground pipeline networks to be installed, this will have a very, very tremendous opportunities out there when we're talking about this complex pipeline network. But for this class, I just want to talk about the sensing and data processing, right? How when we get the data, how we can do the inversion of it. So we can have microwave sensing, we can have capacitive sensing, we can have optical sensing, and how we can fuse that together through the data fusion technique covered by this class. Right, so this is another application. For inversion, we have to deal with data fusion. Particularly for NDE, we are dealing with multi-sensory data fusion. And also, because of physics, we probably gonna deal with the multi-layer fusion and mapping. The multi-layer not only means that maybe the signal is coming from different depths, but the multi-layer here means in physics, we're dealing with different layer of sensing. It can have optical, it can have microwave, it can have low frequency EM, for example, here for the pipeline inspection. And the mapping means that you have to fuse all those data together by understanding the localization problem offered either by the sensing system or the robot. You can read more about this also public available or released technical report from government agencies. You can search you know, if you not find it, I can direct you to the right database. Because it's a you know, government funding, so you know, a lot of material is going to be in public, so you can read that in detail. But this approach tells you that how inverse problem and data processing will be critical in complex systems, NDE and monitoring, where you deal with multi-sensory, multi-layer data. I'll skip this. I believe this is a project Professor Udo mentioned, I believe, for the prosthetic heart valve detection, where you can use EMAT, electromagnetic acoustic transducer system, right? And this is still in a very active fields in a lot of applications when we deal with EMAT sensor development and sensing and data processing. But this is one particular application for biomedical problems. This is for case hardening adapts characterization using nonlinear eddy current. Instead of using linear or make the eddy current work in the linear field, a linear domain that you can generate nonlinearity signals by introducing, for example, high mu materials in the sensor design. Then you can actually understand the case hardening problem there. Just one show of data. Okay, I think I will try to wrap up the morning session, but we still have like 25 minutes. But I want to have like 2 minutes wrap up here. Then we'll start talking about you know, data processing, particularly on some quantification. So this is actually a milestone of our AM morning session. Is let's try to understand where the forward and inverse problems defined and what the roles of that in NDE. Okay, we have to deal with different NDE sensors. You've seen that in the first course. We have to develop new sensors to get new information by understanding the emergent materials, by understanding the new structures and systems out there, by understanding if we want to do this in a local way, like NDE measurement, or you want to do this a global way, called SHM. Sometime, or most of the time, it's going to be a sensor network, a distributed measurement and computing, right? For different ways of doing that, you can have different methods. You've seen most of them. And of course, it's not our intention. It's also not possible for Professor Woodpond and I to cover everything in physics within 10 days. That's impossible. And the human brain will not digest everything well in 10 days. But this lecture series is going to prepare you. Of course, you can watch these videos again and again, but more importantly, I hope this can open a window for you to look into the problem you're interested in the future. And you have a lot of keywords here, a lot of technologies here in terms of sensors, right? Some of sensors, even I'm not an expert. For example, for FBG, we have another professor in our group doing optical sensing, right? So depends on your expertise, depends on your interest, and you can define your solutions accordingly. But anyway, you have different sensing techniques here. Then you will have, it's still blocked me. You'll have your data, right? You have your data, and this is a forward problem. Now, you'll deal with inverse problem through data analysis. For example, image signal processing, data fusion, and so on. You want to understand the data. You want to understand the data by interpretation, visualization, and quantization of the data, right? And you can do diagnosis for NDE problem, right? If you're not doing an NDE problem, you're probably going to also do the same thing. You have the way to collect your data, then you want to do the same data, similar data analysis. The only thing different here is you're not dealing with damage. But when you have the diagnosis, here damage diagnosis, then you want to do prediction. You want to understand the damage severity through the prognosis by estimating the residual useful life. You want to estimating, the damage index over time, and so on. For problems, simulation, for example, finite element analysis, will help you to not only generate the data for your data analysis, right? There's a forward problem. It generates data. It will also help you to do the prognosis, where we talk about model-based prediction or prognosis. While for the modeling, it can be physics modeling. That's what we do a lot as NDE people. It can also be a lot of modeling where civil people, mechanical engineering people do, for example, understanding the fraction mechanics of it. Well, if we can combine them together, then we have a holistic understanding of the physics problem. Well, the model can also help us to understand the data analysis in terms of its uncertainty. Well, one way of doing uncertainty or detection problem in NDE is the concept of POD, probability of detection model. So you want to tell, okay, I can detect this with 90% of POD by given these constraints, for example, the limits of probably false alarms or missing and so on. So simulation or numerical analysis will also help us to do the uncertain quantification, for example, through parametric study. Well, it will also help us to understand the manufacturing problem. And the concept is there for decades called design for inspectability. What's the meaning of design for inspectability is during the manufacturing stage that you want to design some material structural system that is easy for you to get all the data from during the life cycle management. So this is another concept under the life cycle engineering. A key concept here, the takeaway I want to mention in my lecture is NDE is critical in the life cycle management of complex systems. Thinking about using the data analysis you collected from NDE or SHM and help you to manage a complex systems in terms of the cost over its life cycle. And there is a well-known model or analogy called iceberg, right? The way the cost you manufacture or deploy or install whatever systems out there, the cost is only the tip of the iceberg, while the majority of the cost is underwater. That's for the maintenance, that's for the management. And NDE is helping you to achieve an optimal management of those assets or complex systems. So without NDE, there's no way to define the manufacturing innovation because everything you manufactured, you should have a way of testing it. And you have to have a better way of quantitatively test and evaluate through NDE, then you can have a true innovation in manufacturing. Well, we'll have to deal with the interaction between uncertainty quantification versus sensors. So you can improve the sensors through optimization, and you can also have POD to guide the manufacturing. So you have a more, data informed or physics informed manufacturing during your production of materials and structures. So that's what I call the physical model based or data driven, and you see a lot similar concepts out there, but this is the vision that I believe, or what Endel and Michigan State will believe, to make this complete in terms of sensing, data analysis, inverse problems, manufacturing, and statistical analysis. The two lectures you are learning here is going to cover the sensors part and cover the data analysis part, prognosis part. We'll briefly touch the simulation, numerical analysis. I will also touch the uncertainty quantification at a later lecture this afternoon. Manufacturing, we won't be able to cover that, but you'll see a lot of ongoing lectures and research efforts out there. I'm sure you'll find that's actually a very interesting topic. And each elliptical here can be a research domain. It can be multiple PhD theses there, and maybe more. So this is a very interesting, vibrant field that I just want to tell you the big picture, and hey, find your interest, what you want to work on. Okay, the impacts. The last day, day 5, I talked about the new paradigm of NDE. And today, I just want to show you some of them. For example, we're going to have a new paradigm of manufacturing innovation. We're going to talk about new NDE here, infrastructure planning, development, and monitoring. We can talk about the two concept of smart materials and structures. And where does smart come from? So it comes from the new way of getting the data using new sensors or sensing physics, coming from a new way of data analysis, inverse problems. And we have to take advantage of the fourth industrial revolution. I will also cover that in day 5, that how we can combine mobile computing, sensor networks, robotics, Internet of Things infrastructure, and what we're doing here in Industry 4.0 to achieve this paradigm shift. Another thing I want to mention, this is also something what we're doing at Michigan State, and I'm only a small part of it. It's called precision agriculture. And I believe this is a great topic for a country like India, China, Europe, that we have to feed more people with less resources, right? So that's something that that we have to deal with, and I think the philosophy here will definitely fit into this domain. A few examples, for example, you've seen this carbon fiber reinforced polymer, GFRP as well. Composite used a lot in the aviation, aerospace industries. This is a Michigan State racing car, formula car, where we have the carbon fiber composites there. You'll see tons of applications there. I'm sure you see a lot of applications in the first course there. Also, we can have consumer electronics or here part of the devices, for example, your cell phone, to develop NDE devices. You can see the cell phone has a Spartan logo, NDEL logo there, where we convert the cell phone into a NDE device that you can use a phone jack there, a 3.5 millimeter jack there, and you can use that to power your sensor and take the measurement. Use the cell phone as a computing hardware, do the data analysis and visualization there. Internet of Things, that will touch that in the day 5, and smart agriculture. And I will use one example in the root imaging to cover that. So that's the overview of this 5-day lecture, and I think I'm 11 minutes ahead of schedule for my morning sessions. And I hope the pace is good. I actually would like to slow down when we talk about fundamentals and set up the background well. And when we talk about the more details, sometimes I'm probably going to speed up. But anytime you feel free to ask questions. I think, as I said, this is a small classroom. Although I'm not in the classroom, I hope I can be there so you can see my gesture. You can see my, I can also see your reaction from your facial expression. I think that's very, invaluable that for the interaction. But unfortunately, I can see your facial expression. But yeah, hey, feel free to ask any questions so we can have a better interaction. So okay, I think I can probably stop here so we can continue in 2 hours and 10 minutes. In the afternoon, I'm going to talk about the uncertainty quantification fundamentals. And we'll have the uncertainty quantification covered in examples more tomorrow on day 2 morning session. And afternoon, I also would like to spend probably 30 minutes talking about the lab sessions. So you can download the tutorial and codes for the electric impedance tomography lab assignment 1. So you can start working on that in the afternoon. Okay, with that, I think I can stop here. We're 9 minutes ahead of time. I think I still talk a little bit faster than what I expect. But anyway, I hope I conveying the fundamentals of inverse problems and with some examples. Hopefully you guys are motivated to continue this 5-day course with me. With that, I'll stop here. Happy to take questions before we adjourn and see each other in 2 hours. Any questions, any comments, any feedback? Do you like the way that do you like the pace that we conduct the lecture? Do you guys think this is good, or this is too fast, or too slow, something like that? Okay, no feedback here. You guys are quite shy.
Hello.
Yes.
Yeah, am I audible?
Yes, you're audible.
Yeah, actually, I was trying with a different this podium mic, but it didn't work, I think. Yeah, the session was nice. And if any questions from the student?
Yeah, any question? Okay. Okay. Anyway, you guys will see me for the next 5 days. So anyway, any questions are welcome. If no questions, I would like to adjourn so you guys can have lunch, and I will see you in 2 hours and 7 minutes then.
Yeah, that is
Yeah.
2:30 local time.
Correct. Yes.
Yeah. Yeah. Oh,
Okay.
okay. Yeah.
See you guys.
Yeah. Thank you. Thank you.
Yep.
So we'll rejoin at 2:30 in the afternoon.
Compute